Okay, Shabab, as I said, today we would like to discuss the compensation using root locus. We will be limiting ourselves due to the time constraint to the phase lead design. Okay. Well, so basically, what we have covered before is the frequency by using the body plot, and now we will go to the root locus. The difference between the two, in the body plot approach, we usually at the beginning we satisfy the steady state error, and then we will do the design. While in the root locus, no, we will do the design and then we check if the steady state error being satisfied or not. If it is not, then we have to do another iteration. Even though the root locus approach is easier, but it needs sometimes more than one, iteration. Okay.
So it's a trial and error.
You can say so.
Okay.
Look, it's always, there's always, look, there is advantage and disadvantage in anything. Okay. Yes, it is, you can say trial and error. If you are lucky, you get it from first time. If not, then you have to tune it a little bit. Okay. So the closed loop, basically, if you remember, the root locus, we have taken the root locus, and let's say our compensator, suppose our compensator is K. And suppose, I have, suppose I have the root locus for this system, which is going to be something like this. And this way. And I need, the specification is given to me. It will give me certain roots of the closed loop system, and they are located here, in this point. If this is the situation, by varying K, I can, reach that desired one. The problem is, what will happen if I have it not in, it is not within the, reach of the root locus. By changing K, I mean, I will not be able to go to this point. In that case, if this is the situation, then what we need to have, a compensator. Okay. So basically, let me translate what I have said into this graph. In here, I have 3 poles of the open loop system. This is 1, 2, and 3. And based on that, this is the root locus. If I need, okay, if the desired, okay, or the specification produce pole A for me, then I can do it by, as I said, by pure gain. If not, then I need the, a compensator. This is the corresponding time domain for the both points. B is faster. Why? Any suggestion? Why B is faster?
The frequency is larger.
Because what?
Frequency is larger.
No, not the frequency. It is basically this. Okay, remember any pole. Okay, let's say S equal to, let's say minus sigma plus J, let's say omega, or let's say alpha. Okay, now sigma for this one is far away, and sigma will translate into how fast it will decay to 0. The sigma in here is definitely in here, this is more far away from the point A. That's why the response is going to be in this way. Anyway, so let's see what's the effect of adding a pole to a system. By adding pole, usually the system becomes more unstable. For example, if I have a system which has one pole, so this is the root locus of the pole of the system. Suppose I add another pole. This is the original pole, and let me add a pole here. How does the locus look like now for this new system? Any idea? Shabab, the root locus it's required in the final.
Yes, between the two poles, we'll have the yes.
Something like this.
It will go to infinity.
And it will go to infinity vertically. Now suppose let me add one more. This is the original. Let me add two. How does this look like now? This will look.
It's asymptotic.
This will go. Yeah, this will go to infinity. Those will approach each other, and then they break, and they will do like this. So the system become a little bit later unstable. If you calculate the asymptote, you will see that the angle will be of 60 degrees. So that's why it will go in that direction. Okay. Now, how about adding, adding a zero? Adding a zero, okay, pulling the root locus to the left. That's basically, look at this situation. Suppose I have this system. It has the open loop system has 3 poles, 1, 2, and 3. And let me add zeros. If I add 0 at this position, at this location, between the 2 poles, those 2 poles, this is what I'm having. If I add it here, this is what I'm getting, or here. But in all cases, the 0 try to pull the locus to the left hand side. So the question is, can I, add a 0 only? Can we add 0 only? Of course, you have, look, the PD controller. What's the PD controller? The PD controller, we are adding, differentiate. So can we, is it advisable to put a 0 only?
I think no. We should have a
You are
0
right.
on both.
Why? Yes, you are right. Okay. Okay, adding 0 only, it's over problematic because of the controller amplify the noise. Suppose I have a noise in the system. The noise, usually it's, let's say, 0.01. Sine, let's say, 1000 T. If you pass this noise through a differentiator, and this is dn dt. This is a differentiator. What will be the output? So y, which is equal, okay, yn equal to what? It's going to be what? It's going to be equal to 10 cosine 1000 t. Okay, which means that, or minus if you want to, which means that you are amplifying the noises, and this is not desirable. Okay. Well, we said adding pole by itself, it is problematic because it could make the system unstable. So the best way, you will add pole and 0 together. And this is what you have. And what does this represent? What type of, what type of compensator if the zero near the j omega axis? Lead compensator. While this, if P is near the j omega axis, it's going to be lag compensator. Okay. Any questions so far? This is the, you know, I mean, this is the why the what's the meaning of lead and lag, and we explained it before. So lead compensator, this certain comparison between the two, even though we are not going to discuss the lag in this, unfortunately, we cannot. So suppose I have the lead compensator and I want to design it through root locus. So again, in the design, we have to find the zero, the pole, and K. Remember we said in body plot, we start by designing K. Then the pole and zero from the, you know, compensate after correcting the steady state error. In here, no, we will start by the zero on the pole, and then later on we'll go to the K. So suppose, you know, suppose you have, suppose you have a system and you translate the specification into, you know, a pair of complex conjugates. You locate the pair of the complex conjugate in the S-plane. Okay, then the first thing you will do, you sketch the uncompensated root locus. If it is passed through those desired one, then you are done. There is no need. Pure K can do the job. But if not, then basically what you will see, if, you know, those are not on the locus, I have to add a zero and a pole. The location of the zero will be just under the desired complex conjugate pole. So we will pose this is the zero. This is, or just, you know, I mean, immediately after, below it, or just, you know, shift it a little bit. Look, I need S plus Z, S plus P. So I'm already done with Z. So it's very straightforward. Very simple. Just find Z and you read it. Okay. Next thing, I have to determine the pole of the system. Look, I don't know where is the location of the pole. Suppose the pole somewhere in here. Now, by applying the angle condition of the root locus in this desired one, I can determine theta P. For example, in here, I have this is the original system. I have 1, 2, and 3 poles. And now I'm adding to them this zero and this pole. What I am saying in here, so the angles which I am going to have in here, let's say this is theta 1 or theta P1, okay? And this is theta P and theta P2. And I will have one in here, okay? Theta, let's say P3, and the 0. Then in that case, I will have theta z minus, okay, theta p1 plus theta p2 plus theta p, okay, equal to minus 180 or 180. This is known, this is known, this is known. The only unknown is this one. Find it. Any question here? Okay. Once I find it, can I determine, let's say, this distance? Let's say x from here to this point. Can I determine x if I find theta p? Can I determine x? Shabba, what happened? As we move in Ramadan, Shukrikum, you are getting tired, weak and tired.
What is it, Doctor?
Look, this is known.
We forgot about it.
This is known because I know the location here. So tan theta p equal to, let's say, call this is y over x. Y is known, p is known, then x will the only thing which is unknown. Then the coordinate of p equal to x plus this distance, which you already know, because we know the location of the pole. Okay. So this will be also known, and then we are done with the, okay, we are done with the finding the location of the pole. The only thing left is the error constant. Again, apply the, add the, this one, G, let's say G P desired, the desired pole, or desired location, P desired, equal to 1. From the applying the angle condition in here, sorry, the magnetic condition in this point, I can determine K. Okay, let's, with this K, if you are lucky, it will, satisfy the, the desired, I mean, suppose you need 0 steady state error and this, or very small steady state error. If this K will do the job, that will be great. Otherwise, you have to relocate your poles and zero a little bit differently. Okay. You reiterate by, figuring out, first of all, the Z and then determine the P. And you do it in more than one step. Okay, let's take an example. Suppose I have a system 1 over s squared in here. Okay, and I would like to put a compensator. Okay, what are the poles of the open loop system? And where do I position them? What are the poles of the open loop system?
0. Double
At 0.
pole.
I have 2 of them. And how does the locus look like? If I have 2 poles only at the origin. They will go up and down because in here, this is not part of the locus, this is not part of the locus. So they must go on the j omega axis. Okay. This is the locus. Suppose now I want my system to have a settling time of 4 seconds and percentage overshoot of 35. can I translate this information to get the pole of the second order system? Remember the transfer function of second order system, the closed loop one, equal to omega n square, s square plus 2 zeta, omega n s plus omega n square. And what are the poles of this system in here? This is equal to, can you tell me? Do you remember?
minus zeta omega n
Exactly. Plus or minus j omega n root of 1 minus zeta square. So what I want to do, I want to translate the requirements into the pole location. What will be the percentage overshoot will give me? Which parameter?
Zeta.
Or omega n? It will give
zeta.
zeta. So there is a formula for it, you can calculate it. If you do the calculation, zeta is going to be 0.32. Usually, we would like to be in a better situation, we take it a little bit more. So let's take it zeta equal 0.45. Definitely, the larger zeta, it will satisfy the 35% because the larger the zeta, the less overshoot. So suppose we select the zeta. Okay. Now, from here, can I determine what is S, what is omega n?
Yes.
Omega n, look, omega n equal to basically, well, look, before we go with the 4, so it's going to be 1 over, okay, zeta. In any case, minus zeta omega n, clearly zeta omega n equal to 1, which means that I have, this is minus 1. Plus or minus, if you calculate omega n root of 1 minus zeta square with these value, it is approximately 2, J2. Okay, so my desired poles location at minus 1 and plus or minus J2. Now, let's take, okay, this is the root locus of the open loop system. And, you know, the scale in here very little, but assume that, you know, so the location, let's say, the location of the poles are going to the desired one here and one here. And definitely they are not on the j omega axis. So, do we need a compensator? Definitely,
Yes.
we need a compensator. And if we add those two, okay, this is the original system. I have 2 poles, and now I'm adding 1 0 here and 1 pole here. The locus is going to be, this pole will go to this 0, and those, they will bend and will go in this direction. And we would like to force it to, have 1 pole here and the other one in here. That's minus 1 and J2. Okay. Now, we said we place the 0 of the compensator just below the dominant, okay, poles. So what will be the value of the z? What is z equal to then? Where do I locate the 0? We said just, below it. This is 1, and this is 2. So the coordinate of this one is going to be -1 and 2. Just below it is -1 on the real axis. So I'm selecting z of the compensator to be at -1. This is the procedure. Any question here? Now,
Doctor, why you choose -1?
what do I mean by -1?
Why you choose -1?
Oh, this is the procedure. They said, okay, it is, look, the design is by trial and error. They came up with the procedure. I locate, this is what we have said from the, look, this is the procedure which they gave. Okay. Yes, list of the specification. Then, if it's satisfied, fine. If not, if the compensator is needed, place the 0 of the phase lead compensator below the desired root location. So it is just given to you that, if you have this is desired, just position the 0 here. This is what we have said in here. Just position it here. So this is this distance. So now the 0 is known. Okay. Look, you have pole and 0. You have one. Find the other. Okay. Now, so this location is known. The unknown is the P. Where do we position the P? And we said we will apply the angle formula. So what are the angles? I want to apply the angle formula at this location. So the angles, I have 2 poles in here and 1 0 here and 1 pole in here. So what is the angle between the 0 and the desired pole? This is, look, similar to, you can think about it, similar to how do we find the departure angle in a complex conjugate pole. Okay? So the angle formula, okay. How do I calculate this angle, by the way? How do I calculate this angle? How do we find this angle? Any suggestion? How do I find this angle?
Sigma A equal
Okay.
theta A, theta.
So basically, look, the angle is going to be, because this one, I will determine this angle and then subtract from 180. So it's going to be 180 minus tan inverse of the height, which is 2 over 1. Isn't it? The height over 1. And if you calculate this one, it's going to be 116, and I have 2 of them. How about this angle? What is this angle?
Well, it's beneath the point that we are looking for, so it's 90 degrees.
90 degrees, exactly. Okay, so look, we don't take this one. Why? This one,
It is the mirror.
it is not, okay, yeah, no, it is, this is not a pole in the system. Those are the pole, 1, 2, 0, and this one. Those are a desired point. So the angle condition will be 90 minus 2 times 116 plus theta p equal to minus 180 degree. So the only unknown is theta p. If we calculate it, theta p is going to be 38 degree. Okay? If this is known, now can I determine this distance from here to here? Let me call it x. What's x equal to? What's x equal to? Look, tan 38 equal 2 over x. So x equal to tan 38 over 2. Then what's p equal to? P equal to what? The magnitude of course, you will add the minus sign because it's in the second quadrant. What's p equal to? What's the location of p? The coordinate of p.
Doctor, shouldn't the x be equal to 2 over tan 38?
X will be, you are right, yes. Yeah, you are right. Tan 38 equal 2 over, over x. Yes, you are absolutely right. Thank you, Zuhair.
You're welcome, Doctor.
Okay, so p equal to x plus 1 because from this point to this point it's equal to 1 and take it to be negative. So if you do this calculation, it's going to be, this is what we have. Now, what I want to do, I want to calculate, okay. Now look, if you want to, for this system, what will be the steady state error for step input? What will be steady state error for step input? What is the system type?
It's type 0. Wait, no, sorry, type 2.
Type 2. So the steady state error for step is 0, for ramp is 0. If you want to find the steady state error for parabolic, then we need to calculate Ka. But to start with, I would like to calculate, okay? Let me calculate the gain at this point. The gain at this point, so I will take G of, let's say, minus 1 plus J2. This must be equal to 1. Remember? Either you substitute, and your transfer function now, in this case, it's equal to what? S plus Z, S plus P, and S squared. You substitute in here, get the magnitude. Or, look, this is the same as taking the distances from those two poles to here, from this 0 in here, and from the pole in here. Okay? Look, basically, if you want to do it in this way, what do you have? We have, okay, what's the I will have what? Minus 1 plus J2 plus the Z at what? 1 over, okay, minus 1 plus J2 square times minus 1 plus J2 plus 3.6. this must be equal to 1 times k. So look, this represent what? The upper. This represents the distance from the pole and the 0. So this is the same as k. What is this distance? Can you tell me? What is this distance? From here to here. Shabab, just read it.
2.
It is 2. How about from this point to this point? Apply Pythagoras theorem. So what do we have? I have 4 square, because this is the height, will be 2. 2 square, which is 4, plus 1, that will be 5, under the square root. But I have another one with it, multiplied by it, so I'm going to have 5 times, what is this distance? What is this distance? This is equal to what? The height will be also root of 2, this 4 plus, from here to here we said 2.6 square, and find k.
3.6 squared.
No, 2.6. The distance from here to here.
Yeah, of course.
Okay. So that will give you k equal to 8.1. If I need what's Ka equal to? Ka equal limit as s goes to 0 of s squared of s plus 1, s plus 3.6 times k, of course, and k, which is equal to this. There is square in here. The square will go with the square, and you will have what? You will have k over 3.6. Okay, so 8.1 over 3.6. That this is basically your error constant. Any question?
Doctor,
Yes.
in the angle, you multiplied 116 by 2. Why is
Yes.
that?
Because remember, in here, how many poles I have? I have 2 poles. There are 2 poles. Each one,
Yes.
okay, contributes 116.
Thank you.
Sure. Okay, Shabab, there is another example, but I don't want to, I will leave it for you. What I'm trying to do now, I'm trying to go quickly to what did we cover in this course, just to jog your memory of what we have done, okay, in the course. Well, شكلي أنا okay, now let me share. I have only I thought I closed this. Okay, we have few minutes, so I will try to go quickly to summarize what we have done in the course. By now, you should be able to, recognize the response of first order and second order system. This is straightforward. We also talked about the models of, simple and complex systems. For example, the model of physical model of the circuit, the DC motor, the some of the mechanical systems. Okay. We talked about the transfer function model, the state space model, okay, and and differential equation model. Then later on, we talked about the stability. So by now we should know how to, check if a system is stable or unstable. We talked about the steady state error, in particular for the three types of input, step, ramp, and parabolic. We talked about the system types as well. We designed controller by using either the Nyquist, either the body, okay, in the frequency domain, or root locus. And I hope you gain from the course, not necessarily from myself, from the lab and the homework, how do you utilize MATLAB in manipulating, systems. Let me go quickly. This is, in general, this is what we have covered. Let me go and remind you about the topic which we covered. This is, there is nothing new. I just pull it from the, slides which we have in the course. Well, first of all, we talked about the mathematical model of system. You have a system, you have a circuit, or you have a DC motor. We try to have the mathematical model. Basically, you would like to have the differential equation for the system, or from differential equation, you can go and talk about, transfer function, or you can talk about the state space. In order to do analysis, you must know what is the system, what is the model, okay? Because without the model, you cannot, you cannot understand and you cannot design any controller for the system. Okay. We said in doing the modeling, we use, if the system is physical, we use the physical law, like, Newton's law or KVL, KCL in electrical system. Okay. And remember, we talked about the three model and how they are, interacting with each other. How do I get each one from the other? The basic one is the differential equation. For any system, we start with the differential equation. Then, by taking Laplace transform, I can go to transfer function, or I can go to the state space. Between those two, also transfer function and state space, we can go back and forth. We said, if I have state space, I go in this way, I have one system, unique. But if I go this way, I will have infinitely many state space representation for the transfer function. We talked about the, block diagram, where the block, basically, it has an input and output. This is black box. You can, put whatever you want in the black box. This is for single input, single output. We talked about also multi-input, multi-output. If the block diagram is complicated, we either use block diagram reduction, or we could use, the Mason's rule, which is signal flow graph. We also talked about the state space representation, and we said the state space representation is little bit, it will give you more information about from the transfer function model. And of course, if you have transfer function, you can go always to the state space. Then we talked about the solution. If I have a differential equation, how do I solve it? Okay. And this is, we covered it. If you go back to your, I don't remember which lecture, but it's there. This is the convolutional integral. Then we talked about the second order system. Second order system, we said they are very important. They, can approximate good number of systems. Okay. And the specification for the second order system are the overshoots, okay, and speed of response, or that's, if I want my system to behave in a certain way, so I should know how much I can tolerate in terms of the overshoot, in terms of the time rise. This is in the transient side. In the steady state, we talked about the, error, okay? Based on this specification, we can come up with a second order system. We also talked about the stability. We started with Routh-Hurwitz, and with Routh-Hurwitz also we talked about the relative stability, how far the poles are from the J omega axis. Then we talked about the stability of the state variable. How do I check if the state variable model is stable or unstable? Any guess? In the transfer function, I look into the pole of the system. What about the state space? Any guess, شباب؟ ولا خلاص يعني by now?
again دكتور.
How do you find whether a system is stable or unstable if you are given x dot equal ax plus bu, y equal cx plus du? By the way, this is, this part of your final.
We should go to the transfer function model.
No, not the transfer function. You find the eigenvalues of the system. If the eigenvalues of the system are in the left half plane, the system is stable. Otherwise, the system is unstable. So we use the eigenvalues. Okay, we talked about the root locus. Then we talked about the body plot and phase margin, gain margin from body plot. From the body plot or from at the beginning, we can get the error, Kp, Kv, Ka. This is, we have done it in the body plot. We talked about the Nyquist plot and Nyquist criterion and how do we use the Cauchy theorem. And this is another example in finding the, gain margin, phase margin. Then the PID controller, unfortunately, we did not have much time to talk about it, but, I assume in the lab you have taken it. Then we talked about the, the design, okay? The design either from the body plot, and we cover the lead compensator and lag compensator. The phase lead lag, unfortunately, we don't have time. Then from the root locus, we, did the design of phase lead. The phase lag, unfortunately, usually I cover it, but unfortunately, we couldn't do it this time. So look, I hope, you gain from the code. This is basically what we have done. And I hope you gain something from it. I enjoy teaching it. It is in your section, there is good interaction. I really appreciate the interaction. And I wish you all the luck. I will be available for any question. If you have any question, we can have an appointment and we'll have a meeting. Okay. The exam, as we said, is going to be May 5th. So good luck in your exam. One more request, Shabab. The evaluation, it's not compulsory, but it will be good to have it. It seems to me not many of you have done it. If you can do it, please do it. If you think you cannot, that will be fine too. Okay. So anyway, thank you again. And I wish you good luck in the final.
الله يعطيك العافية دكتور.
الله يخليك.
تمام.
شكرا